Hi everybody, welcome to the second half of our statistics course. In the first half we learned a lot of different concepts. We studied probability and distributions, and we kind of prepared for the second half of the course where we really get into what statistics is. And I want to start this week with the new chapter here, chapter 10 on estimation using confidence intervals. I wanted to give you an introductory video to kind of show you what this is all about. So this should help you as you do the next two homework assignments. So here we go. So before we talk about confidence intervals, which again is chapter 10, I want to go back to the homework you worked on chapter 9. And so you guys did a number of exercises here. I want to go down to problem 11. It says a variable is normally distributed with a mean of 120 and a standard deviation of 5. So you should have a picture in your mind when I say that by now, by the second half of the course. And I'm going to go ahead and show you a picture. Right? So here's a bell curve. The mean is 120. The standard deviation, which will take you to about this point of inflection here, that's 5, let's say. So there's a picture. And it says 4 scores are randomly sampled. What is the probability that the mean of the 4 scores is above 127? Okay, so I'm going to go back to my paper here, and I'm going to point out that a symbol we have for a mean of a sample is x bar. And so I'm going to let x bar be the average of these 4 measurements that I took. You know, I was thinking about this problem and I said, well, what might this represent? Suppose this is 120 volts, like when you plug into an electric outlet in your home, those are usually 120 volts. But I suppose when they tell me it's 120 volts, is it always exactly 120 volts, or is that some kind of an average? Maybe it is, okay? So one thing that I've learned how to compute, even before that chapter, is I learned how to compute the probability that x is bigger than 127. And I understand that probabilities are the same as areas. So what I would do is I would say, how much area do we have to the right of 127? Right? And that probability, well, it's less than 50%, I can see that. But if I want to know exactly what it is, and you learned how to do this a couple chapters ago, we have these really nice calculators in this course. So under calculators, if I go to the normal distribution calculator, right? This is basically the picture that I just drew. Although this is the standard normal distribution, this is what we call Z. I want my mean to be 120, and I want my standard deviation to be 7. And I'm looking for the probability that oh no, the standard deviation was 5, excuse me. And I'm looking for the probability of being above 127. And it tells me that the probability is about 8%. Right? So if I go back to the paper, 0.0808. Now this is not the answer to problem 11, because problem 11 said, if I go back to that problem 11 said, find the probability that the mean of the 4 scores is above 127, right? So, you know, if you plug in to 4 different outlets and take some measurements, what's going to happen? Well, you know, maybe my 4 measurements are 119, 122, 128, and 129, or something like that. Even though the mean is 120. By the way, if this happened, I think if you did the average of these, this average would be below 127. So
it might be true that one or two of these things are above 127, but for the average to be 127 is actually a little bit more difficult. And this was related to the fact that the standard deviation, okay, for the means ends up being x over square root of n. So again, the way we wrote that was the standard deviation of the means is the standard deviation you had over the square root of n. Okay, so in my example, the standard deviation was 5, n was 4, so it's 5 halves, which is 2.5. Okay, so if I want to solve problem 11, I can use the inverse calculator, but I should use a different standard deviation. My standard deviation should be 2.5. And so I'm going to go back to my calculator, and we're going to use 2.5 as the standard deviation and do the calculation again. And if you look, it's very unlikely, less than 1%, 0.0026. It's extremely unlikely that when you sample 4 of these, you would get a mean bigger than 127. This is why when you do experiments, you repeat them, right? As a matter of fact, we're going to try and turn the problem around today. Suppose you had a sample of 4 measurements and your mean x bar is, suppose we know it's 127. The question is, what do you think the population mean is? I'll tell you what you might think. You might think, I don't think it's 120 anymore. Because this is a very unlikely thing to happen. It happens less than 1% of the time. Okay? So there's a way of quantifying. See, this is what's called a point estimate of the population mean. By the way, just like we use x bar for the mean of a sample, there's a symbol for the mean of a population. And the mean of a population, we use the Greek letter m, which is mu. And you've seen mu before. That's the same thing we use down here for the mean of the distribution. So today I'm going to have a sample. By the way, this is called, okay, a statistic. A statistic is a number that is associated with a sample. Okay, so again, a statistic is a number associated to a sample. And you know how to find lots of different statistics at this point. If I give you a sample of 4 measurements, you could find their mean, you could find their variance, you could find their range. There's a lot of things you could find. Okay? Well, what happens is we hope that this is close to that. But what we do is we kind of not just take 127, but we want to cast a net to either side of 127 to capture the mean, you might say. And so today we're going to be doing what's called a 95% confidence interval for the population mean. Okay, so how does this work? Well, what happens is you're trying to capture mu, and you will say it is going to be between x bar plus the margin of error and x bar minus the margin of error, where we need a formula for the margin of error. And the formula is going to be different depending on what you're trying to catch. So E here is going to be in general, a critical value times what we might call the standard error. Now, down below, I talked about the standard error of the mean. So we had, I called it sigma x bar. I think your book calls it sigma m, right? Let's take a look at that just to be sure. Yeah, they say the lower limit is z 0.95 and z 0.95 times sigma m, right? So they're using m instead of x bar. That's the difference. X bar is more of a standard thing to use. So we want the z value corresponding to 0.95. And the reason I put 0.95 is because I said that we're going to construct a 95% confidence interval. So let's learn how to get these measurements. Well, for sigma x bar, okay, the standard error, I guess it depends what we know. So in our example, we know, well, actually, I guess I have that from down below, right? I computed that it was 2.5 because it was 5 over the square root of 4. Okay, so for now, let's pretend we know that. Let's say that we know that this is 2.5, okay? And I'll tell you that in general, I guess that wouldn't happen, but we'll get back to that. So we have 2.5, and now what is the z-score corresponding to 0.95, a 95% confidence interval? Well, just like we used the normal distribution calculator to compute this area, we've also done problems where we go backwards. And so I need to show you how to do that once again. You're going to click on the calculator called inverse normal distribution. And so this is one that you can specify an area and a mean and a standard deviation. So my area I want is 0.95 because we want 95%. And we're going to click on the one that says between. And notice it says between 1.96 and negative 1.96. You have to make sure that your mean is 0 and your standard deviation is 1 when you're looking for these z-scores, these critical values, right? Because that's how it works. The standard normal distribution is this. And so we are just under 2 standard deviations. And so if I go back to my paper, the z-score I want is 1.96, okay? So we can compute the margin of error. Get out a calculator here, and we will go ahead and work out that margin of error. So if I take 1.96 times 2.5, I get 4.9. Okay, so that's the margin of error. And so my 95% confidence interval, the way I would write my answer, I'm going to say that mu is between, now x bar was 127 plus 4.9, and this is 127 minus 4.9. And so there's a couple ways we could write it. We could write that the population mean is somewhere between 131.9, and if you subtracted, you would say, well, this is 122.1. Sometimes you'll see confidence intervals written in bracket notation. There's a couple different ways that they write them. But basically, what we're saying is, we think that the mean of the population is between these values. And then there's this expression, 95% confidence. What does that mean? I'm 95% confident that this will be true. You know, it's funny because we're used to, there's a 90% chance of rain today. What does that mean? That means bring an umbrella, right? I guess we're saying we don't think the mean is 120. Now, there is a chance that what happened was maybe the mean is 120, but I just happened to get a bunch of big data points when I did my sample, right? What the 95% confidence really means is that if someone else does a sample of 4 and computes their confidence interval, and someone else does it, let's say 100 different people do this, we would have different confidence intervals because we would pick different data points, we would make different measurements. But in 95% of those, we would capture the true mean. That's the idea. Well, what if you want to be more confident? What if you really want to be sure that you capture the mean? Well, you could do a 99% confidence interval. And actually, this is a good exercise for you. See if you can understand what's going to happen. Well, maybe I'll do this in black. Mu, again, is between x bar plus e and x bar minus e. X bar we said was 127. What's going to change is going to be e. When you come over to compute e, remember it's the critical value times the standard error. I'm saying the standard error is 2.5. We calculated that earlier. But what will change if you change the confidence level is you will change where the critical value is. So let me go back to that inverse normal distribution. And let's change the area to 0.99 and see where the critical values are. Negative 2.576 and positive 2.576. So that's different. So if we go back to our paper, and if we put 2.576 here, okay, so let's try that. 2.576 times 2.5, which was our standard error. Now I'm getting the error is 6.44. And so that would give me a confidence interval of mu between, well, that'd be 133.44, and this would be 120 if I subtract 6.44 from there, 0.56. So that's my 99% confidence interval. And that means in all but 1% of the intervals constructed this way, we would capture the true mean. Remember, I thought it would be very unlikely that 120 was really the mean if my sample has 127 values. Now there's a problem with what I just showed you, and that is I claimed to know the standard error. And if you remember how we computed the standard error, well, we took the standard deviation of the population and divided by the square root of n. Now I know what n is. N is 4. I had a sample of size 4. But in general, there's no way that you're going to know the population standard deviation if you don't know the population mean. I mean, it's kind of silly. And this is the point of the t-distribution. It's that we want to make an estimate of the sample error. So I'll tell you what we're going to do. Let's suppose again we have 4 measurements, and suppose we know that the average x bar is, say, 127. Okay. I suppose I should also know what the standard deviation is if I'm going to talk about the standard error of the mean. So I'm going to go ahead and try and come up with an example for you here. So as I was trying to create an example for you, I decided, oh, we should use the Google Sheet. So you might remember that there's a link to estimation using confidence intervals. This will be helpful for you in the chapter. Of course, you want to make a copy. I already did that. Remember, you want to make a copy of estimation. And down here at the bottom, there's instructions. There's estimation of the mean, and that's the homework for Wednesday is going to use this. Estimation of proportion, estimation of variance and standard deviation, okay? And so I want to show you that you can use this calculator to do all the calculations we just did very quickly, okay? And so let's go back and look at the original problem we had. We wanted to construct a 95% confidence interval for the population mean. Okay, so let's see how we would do that. What you do is you come up here to this first box, mean confidence interval with the population standard deviation sigma known. Remember, I told you that the standard deviation was 5. I told you that the sample size was 4. I told you that the sample mean was 127, and we wanted 0.95 for the confidence level. And notice it spits out the critical value, the z-score. It spits out the margin of error. So let's just compare to what we had when we had a 95% confidence interval. We had over here 1.96 times 2.5. So the margin of error was 4.9. They say 4.89. And then they spit out the confidence interval here from 122.1 to 131.9. And so it does very quickly all those things that we just did. 122.1 to 131.9. And if you want the 99% confidence interval, this will spit that out too. And so I can change the confidence level to 0.99. And there's my confidence interval again, just above 120 to 133.44. So that's nice. But as I said, in most situations, you're not going to know sigma. And so I'm imagining instead that I have a sample of 4 measurements, and the sample mean is 127, and I don't know the standard deviation. Now, how could this come about? I was trying to think about this, and I thought, can I think of 4 measurements that would have a mean of 127? Sure. What if I had 125, 126, 128, and 129? You can add those up and divide by 4, and you're going to get 127. I think that's not hard to see. So I can tell you that x bar is 127. What is more difficult to compute quickly is the standard deviation. There's a formula for that. There's also calculators for that. Let's compute the standard deviation, right? It's the square root of the variance, but rather than do it the long way, let's use the software. And this Google Sheet that I just mentioned can handle data very quickly. So down here below, you can put up to 100 data points. And so I'm going to put in 125, 126, 128, and 129. And the reason all it's doing over here is it's giving me over on the right the mean, 127, like I said, the standard deviation, and it even gives you the sample size because that becomes important also. Remember, n is important. And so sure enough, my standard deviation is 1.8. Well, I'll write the whole thing out. 2574. Okay. And they tell me that n is 4, by the way. So this is n equals 4. And so now if I'm trying to construct, I don't know, what should we do, a 95% again? Sure, let's do a 95% confidence interval. Well, the way that works again is mu is between x bar minus e and x bar plus e. On your homework, I hope you guys are going to be writing some of this stuff down. And let's see, we know that E is equal to, well, it's the critical value times the standard error. Now, here's the deal. When the standard deviation the population standard deviation, which is called sigma, is unknown. And I'm going to say usually the population standard deviation is unknown. Then, in that case, we need to use what's called the t-distribution to get the critical value. And the t-distribution looks like the normal distribution, but it's wider. It's more spread out. How spread out? Depends on n. When n gets really large, say 100 or more, this is going to look like a normal distribution. You might say, well, it does look like a normal distribution to me. Well, I'm telling you the normal distribution is a little bit taller than the t-distribution. And we have a calculator for it, which we can use to get the critical value. Oh, and for the standard error, I should write down, we're going to use, the sample standard deviation over the square root of n instead of sigma. But for the critical value, we're going to use the t-distribution. So let's go ahead and get the right calculator for that. So of course I have the Google Sheet, but let me just show you how this works here. So if I go down, there's a normal distribution calculator, as we said, but you should use the t-distribution to find the t values. So here I'm going to use the calculator called inverse t-distribution. And it asks me for degrees of freedom. Well, the degrees of freedom is going to be n minus 1. So it's going to be 3, and that's explained in the book in section 2 of this chapter, why it's 3. But it's always n minus 1. And so the t value that I want for this confidence interval is actually 3.182. And you're going to notice that's a lot bigger than the 1.96 I had last time. So we're going to put in 3.182, and then we need to multiply by the standard error. So let's see what that would be. 3.182 times, I'm just going to round this to 1.8, 26 over the square root of 4, which is 2. So let's take our calculator out and figure out what that margin of error is. So let's see, if I take 3.182 times 1.826, and then if I divide by 2, which is the square root of 4, I get 2.90. Well, 2.91, let's say. That's the margin of error, E. And so my confidence interval would be, well, again, this is 127 minus 2.91 and 127 plus 2.91. And so let's see. I'm getting that mu is between 129.91 and 124.09. So this is my confidence interval. And this is more realistic. You're not going to know the population standard deviation, so you can't do sigma over the square root of n. You have to do s over the square root of n in general. S we computed using a calculator. Actually, we used the Google Sheet. Let me go back to the Google Sheet to show you what's going on here. So we were on this Google Sheet. Yeah, we threw the 4 data values in here and it gave me S. But we could also use this information to compute my confidence interval over here. So again, my sample mean was 127. The confidence level I was doing was 0.95. Now it asks for the standard deviation S, 1.82574. Right, that's the standard deviation. And the sample size was 4. And sure enough, I'm getting that the confidence interval here was 124.1 to 129.91. And that's exactly what I computed using the formulas. Okay? So this Google Sheet is really nice, but I think to just hand you the Google Sheet without showing you where the formulas are coming from, you don't learn very much, right? But definitely at this point, to answer most of the homework questions, this Google Sheet should come in pretty handy, I would say. So maybe we can try one more problem and then we'll call it a day. Well, I'll leave you to it. You can still ask me questions, guys. Please don't hesitate. But let's do this. I had another problem that I got. This was actually really cool. I was given these Teaching of Statistics in the Health Sciences Resources portal, and I went ahead and read one of the studies about a smart pill. Okay, and so a couple things that are happening here. They give you all kinds of stuff here. By the way, this study was from Dr. Amy Nowacki, Associate Professor at the Cleveland Clinic. And basically what's happening is they know that, when someone's in the hospital, a lot of times a nurse will ask, hey, when's the last time you had a bowel movement? Well, that's because the time it takes for food to go through, if it's been a long time, that's a sign that things are not good inside, right? And so they came up with this smart pill that they could throw in your food, and they could measure how long it takes until it comes various places. And so I went here and I grabbed the data. I downloaded it in Excel. Okay, so here's my data in Excel. I thought this was pretty nice. And there's a lot of data here. You can see they have group. By the way this is grouped, 0, those are patients that are terminally ill. 1, these were actually not patients, these were volunteers. Some are male, some are female. I forget which one's which, 1 or 0. But they grouped them. They took their height, their weight, their age. And then what they did is they started measuring how long it takes for certain things. So this GE time, and all these terms are defined. Let me go ahead and get those definitions because I thought this was really cool. Smart Pill Data Dictionary. Yeah, this PDF has it all. So it says GE time, gastric emptying time. Time from ingestion until gastric emptying. That means how long until it goes past your stomach into the small intestine. So that's column 7. Let's take a quick look. Wow. So let's look at the healthy patients first to get an idea, right? The healthy patients, the volunteers I should say, it took 2.7 hours for this person to have the smart pill leave the stomach. This person, it took 5 hours. This person, it took just under 2 hours, 3 hours, right? But if you look at the terminally ill patients, look how long it's taking for the pill to actually leave the stomach. They don't have a measurement on this one. This one's pretty normal, right? 4. But some of them, it's really taking a long time, and that's a sign that health is not good. SB time is how long it takes to go from the small intestine to the large intestine. C time is how long until you release it from the large intestine, the colon. They don't have any measurements on that, it looks like. Maybe the battery died. That was one issue they were having with the study, I remember. Sometimes you don't get all the data. But then this is when it actually leaves the body, so how many hours later? So for a healthy person, it might take 50 hours or 22 hours, 23 hours, 31 hours, right? For it to leave the body. For a not as healthy person, it might take a really long time. So this is, again, the total number of hours from when you ingested the smart pill until when it left. So I might wonder, what's the average time it takes a person? And so let me take 10 healthy people. So there's 10 data values. And I'm going to go ahead to the Google Sheet. I'm going to copy those. I'm going to go to the Google Sheet, as I said. And I'm going to paste those 10 data values in there. So I think I can just paste them. There they are. So there's my 10 data values. The mean is 27 hours, but the standard deviation is 14 hours. There's my 10. And now if I want to, I can construct a confidence interval for this. So let's do this. We don't know the population standard deviation, that's for sure. We do know my sample mean. It's 27.597. I can read that below. Let's do a 95% confidence interval. The standard deviation, it says, is 14.1334. And the sample size this time is 10. And so they're saying, oh, the confidence interval is between 17 and 37. So there's a difference of about 20. So again, that makes sense. My mean was 27, and it looks like the margin of error is 10, so I'm moving 10 in either direction. And I'm saying, I think that the population mean is somewhere between there. Now, what's the population? Well, remember the population was all these volunteers. So will the population mean actually be between 17 and 37? I guess I could find it out because I think I have less than 100 volunteers total. Okay, let me do this. Let me copy all of those times. Yeah. So I'll copy all of those times and I'll go back to the Google Sheet. I can put that in the Google Sheet, just see what happens. So what I can do is I can paste them. There they are. There were 86 healthy volunteers, and the mean ended up being 34.8. And notice that is in the confidence interval, okay? Now, it didn't have to be, right? If I happened to get 10 patients that had a really low average or a really high average, maybe I would have missed it. But again, a confidence interval is a net where you think you will catch the population mean. In this case, my population was 100. My sample was 10. Okay, but in general, your population is some really large number. Anyways, I hope this gives you more of a feel for what we're really doing with confidence intervals. And if you have questions, please ask. Bye for now.